Hello, welcome to session number 3 in the series Clocking Circuits. My name is Anurag Nigam, and we are going to have two parts to this session. One part is going to be dealing with multi-modulus frequency dividers. So let me just write out. My spellings may be wrong, and I apologize for that, but you know I can't do anything about it. Multi-modulus frequency divider, or I'll call this as MMFD. Okay, the idea is very simple. Okay, the idea goes like this, that I have a forward path for a T cell. Okay, so let's say this is a T cell, right? And its output basically is going to be toggling, right? Rather, I would say this is a D cell, and let's say this is Q, which I have already marked. Sorry about that. So what I do is I am going to uh, have here, let's say, an XOR gate. Okay, an XOR gate here, and XOR gate is a controlled inverter. Okay, which means that if it's one of the inputs is high, the other input is going to flip. So basically, this is a D flip flop, which is used as a T flip flop, right? So this is the basic design. Now, what I want to do is, let's say I represent this, okay, by a block here, which is AND gated. Okay, so basically I have a D flip flop. So this is a, again I would draw a, so I would say that I have a master and slave, right? So I would say that this is a D latch, so this will be a clock. Okay, so this would be a clock, and its output is Q, so this is a master. And then I am going to have this Q driving the slave with a clock bar, right? And its output is Q, which is, or Q bar also, and this Q bar is fed back in. So now what is going to happen, so this is clock and this is clock bar. So now what is going to happen is, whenever this control input, okay, is high, then there is a feedback on this which makes it a T flip flop, and there is a divide by 2. Okay, so you're going to get a divide by 2. Right. Now what I can do is I can also make another circuit over here, okay, using some circuitry over here, which basically I call swallow circuit. And the function of this swallow circuit is to either enable or disable the control, right? So what happens is, let's say I have a clock which is going like this, right? And the output is going to be toggling on the falling edge. So if it is a divide by 2, this is what's happening, correct? And let me extend it to include more cycles. Okay, sorry about this. Okay, so let's draw some more cycles of clock. Okay, so then it is toggling on every falling edge. So it's toggling here, toggling here, toggling here, toggling here, and toggling here. And let's draw that. So now you see here, sorry about that. Now you see here, this is a divide by 2. Now what if I do the following? I went through a transition here, but the next one, which is basically this clock edge, okay, which basically causes this transition, I swallow. So if I swallow this transition, then this will occur over here. Correct? So when this happens, I have got one cycle. Just draw. I have got one cycle. I have got two cycles. So one cycle over here corresponds to two cycles of clock. Now, if I swallow this edge, then I include a third cycle also. So now here, this has become divided by 3. Right? So this is the principle behind 2 by 3 cell. So I'm going to have a swallow circuit. And what's a swallow circuit? It's nothing but a similar arrangement which is at the top. But then it has got one more input which is called mod in. And then it has got one more input which is called P. Okay. So for divide by 3, sorry. For divide by 3, the mod in has to be high and P has to be high. Okay. So the idea is very simple. If mod in is high and P is high, the divide occurs by 3, else the divide occurs by 2. And similarly, there is one more output which is called mod out, which allows us to cascade this 2 by 3 cell. Right? So if you want to see what this is, that's that. Okay? At the top, you have an AND gated D latch followed by an as a master latch, followed by a slave D latch, which plays the role of a what you call a T flip flop. So it's going to divide by 2. Then there is a swallow circuit which receives mod in, and it works on mod in and P, and it's also a master slave, right? And that controls whether the 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 T input goes in or not, right? So whether the flipping takes place or not. So that's how we are going to swallow a circuit. Now the question is, I can take such cell and I can cascade that. So there is a mod in and then there is a mod out, right? So I can cascade these cells. So in here you see F0, F1, F2, F3, F4 and F5. So there is a spelling, there is some mistake here. F4, F5, F6. Okay. So these are cascaded. Okay. Just like a ripple counter. And then their mods are basically also cascaded back. Right. And then you have got P0, P1, P2, P3, P4, P5, which is going to decide whether that particular cell is dividing by 2 or by 3. Now, if the divide by 2 occurs on the first cell, that is P0, then you have a 2 clock cycle or a 3 clock cycle, right? You have whether P0 is low, it is 2 clock cycle, and P0 is high, that means that there is 3 clock cycle. Now, if the same thing occurs on the second bit, which is P1 is high or P1 is low, so P1 is low, it means that the cell is dividing by 4, right? Because it is rippled, right? Or it is dividing by 6, right? Okay, so if the second cell is dividing by 2, then it is division by 4 or 6. Now, let's say that this cell basically is 1, then this cell is also dividing by 3. Now, how many clock cycles can you fit in one cycle of the second cell, right? So that's the question. So if I was to cascade this, what happens is if I have all the P inputs are 0, then each one is dividing by 2. So that the base count here is 2 raised to 6, right? So that is going to be 2 raised to 5 is 32, right? 6 is 64, right? So this is dividing by 64 if all P0, P1, P2, P3, P4, P5 are 0. Now, if one of them is 1, then that's the additional count. And you count it in terms of the original clock, not in terms of the ripple, right? So when I say the first cell divides either by 2 or 3, the second cell, when divides by 2, that's another story. But when divided by 3, then you have got 2 cycles of the original clock, right? So every time the bit goes 1, it is supporting 2 raised to that bit number, right? So for example, if P0 is 1, then 2 raised to 0 is 1, and P0 being 1, so that is going to be 1. So 1 additional cycle on top of 64. So that is going to be 65. Now, if so, you are looking at this equation, right? So I hope you can see my pointer. So you are looking at this equation, right? So if P1 is 1, for example, then it will be 2 raised to 1, that is 2. Okay, so 2 times of 1. Okay, and then this one, let's say, is also 1, then that is going to be 2 raised to 0, that is 1 and 1. So that will be 2 plus 1, 3. So this will be 3 above 64. So 3 above 64 is going to be 65, 66, 67. So if both are 1, it's 67. If it is 1, 0, for example, then it is going to be 2 above 64. That is going to be 66. So I can create anything. So let's see how it goes. So let's say P0, P1 only. P1, P0. Okay, so let's say this is 0, this is 0. I'm considering only 2 bits. So the count, and I'm assuming all of the bits are 0. So the count here is going to be 64 plus 0. That is going to be 64. If it is 0, 1, then the equivalent is going to be plus 1, right? Because 2 raised to 0 is 1. 1 times of P naught is 1. So that is going to be 65. Now, if I do 1, 0, it's going to be 2 plus 64. That is 66. If I do 1, 1, it is going to be 3 plus 64. That is 67. Now, this can be extended to your all 6 bits. So if all of them are, so the count can go all the way from 64, and if all bits are 1, then that is equivalent to, right? So if all bits are 1, I am going to add 63, right, on top of 64, right? So that will be 127. So this 6-bit divider, which is made up of these 2 by 3 cells, is going to generate a divide ratio from 64 to 127, right? So I hope you understand how this works, and this is something which we are going to generate. So all we have to do is generate this block, right? So these blocks are same, and then just AND gating them, right? Okay, so this design is very simple. Now the challenge comes. Where does the challenge comes? The challenge comes is how fast this can operate. Okay, so the challenge is how fast can this operate. So VCO input is directly driving here. So this is going to be coming from VCO. So VCO is driving that. Now VCO, let's say, is operating at 5 gigahertz, then the first cell has to operate at 5 gigahertz clock in, right? So the challenge comes is how do you design a 5 gigahertz 2 by 3 cell? Okay, one approach can be you involve something called current mode logic. Other approach is I cut down some blocks in here so as to speed up this cell. Okay, so we are going to take both the approaches. Okay, so here I am designing for Wi-Fi 6E. So my input is going from 3.8 gigahertz to 4.8 gigahertz, right? So my input to this divider is going to be this range. Now let's say if I want to divide something like 8.5 gigahertz, which is mostly used in radars, going to 11 gigahertz. Okay, now the same challenge you can see over here. The challenge here is how to design this first cell, which is going to work at this frequency, see back. Okay, now as a designer, okay, you can easily be spoiled by technology skill, right? So for example, if I give you a technology like 22 nanometers or 14 nanometers or 10 nanometers, okay, this is a piece of cake. But if I give you something like 250 nanometer or 180 nanometer, 130 nanometer, is it doable? Yes, it is doable. But then you have to play some tricks. And I'm going to design this in 130 nanometers. And what I want to do is we are working with this. But on a parallel, I also want to design for this. And I want to show you two approaches for designing this. Okay, so let's go ahead and first of all do this part. Okay, so uh, okay, let me launch the software. Okay, so now I am going to create a new cell and I will call this cell as so I need to create these blocks. So for example, I want to create a D latch, master and slave, and then I want to create some gates, right? So what I'm going to do is first of all I'm going to create transmission gates. Okay, so first of all I'm going to make a new category, file new category, and here I'm going to call this category as TX gates, right? And say okay. So I have a new category here. Then I'm going to create a new cell and I'm going to call this as TX cell. TX cell. And this is a transmission cell. And this transmission cell, if you do not know how it works, I will refer you to another play series, which is a playlist which is called Analog Integrated Circuit Design using ADS. So I'm going to go here and say okay. So here I am going to put this in this category, TX gates, right? So I'll say modify and I'm going to put in TX cell. Okay, fine. So I want to do that, and the basic structure of this TX cell is going to be an NMOS and a PMOS connected like that. And there's input A and there's output Q. And when this device NMOS is enabled, that is, this is C, when C is high, then A transmits a 0. So this device is capable of transmitting 0. And when C bar is low, then this device is capable of transmitting 1. So the NMOS transmits a 0 between input and output, and a PMOS transmits a 1 between input and output. So that's a transmission step. And so that happens if C is 1 and C bar is 0, then this A is basically Q, right? So whether it's 0 or 1 doesn't matter. Now if C is 0 and C bar is 1, then this Q is a high impedance. Okay, so what that means is that you can do tri-state buffers. Okay, so that's the idea. So now I'm going to make this set. And another thing is, what do you do with the body connection? Even if the device sits in a valve, do not connect it to A, because you do not want to connect all the bodies to A, right? So even if, for example, a PMOS sits in N valve, okay, then you take the body connection, right, and connect it to VDD. Okay, take the body connection and connect it to VDD. And in this case, okay, take the body connection and connect it to ground. okay, or you can say ground. So that's the basic design of a cell, a transmission cell. That's what we are going to do. Oh, so I would just do it, insert, browse, and I will go to MOSFET, and I will look for NMHP, and I want to make this as 2.8, and these sizes are something which you have to get used to with experience. Okay, 2.8 into 2, that's 5.6. So I am going to rotate this again. It's like that. And notice the source of both the devices are at known potential, and known potential in this case is going to be A, input A. Okay, so now the next thing which I need is going to be a PMOS transistor, right? And this one I am going to do 2.4 into 6. Okay, and somebody would ask me, why these numbers? Okay, and the answer is very simple. The answer is the PMOS has to be 3 times the size of the NMOS, because the whole mobility is 1/3 the electron mobility. That means if you want to source the same current in both devices, PMOS has to be 3 times of NMOS. Okay, so now I'm done with the cell. Okay, and I will do the pins. Okay, and I'll usually keep input output pins. So I want A, and that pin would be over here. Then I want Q, that pin would be here. Then I want C bar, that pin would be here. And then I want C, that pin would be here. And then this is a PMOS. The body connection will go to VDD, and this connection will go to ground. So I have a ground pin which will be connected here. And then I have a VDD pin that would be connected here. So I'll just make these connections. And I want to tell you this. See so many books like, Razavi, and then, all those, Gray Myers and their fellow authors. They have also put these lecture series which are very good for the theory. And you should go through those lecture series to learn the theory. Okay, but when it comes to practical, you need something what I'm doing, because the theory books don't cover the design part or the sizing part. They cover the concept part. So you need to follow this lecture or somebody else's lecture to discuss the circuit design. Okay, so we are done with this TXL. Let me see if I'm recording. Yeah. So next what I'm going to do is I'm going to make a symbol for this. So I'm going to make a symbol view for this. And here my left pin is A, my right pin is Q, my bottom pins are going to be C, D, and ground, right? And the top pins are going to be VDD and C. Okay, so A is covered, QC is covered, CB is covered, ground is covered, Q is covered. Okay, so now I'm going to edit this a little bit. And what I want to do is make a much smaller component, because this I'm going to reuse a lot. So I want to do something probably this small, right? And that would mean that I can move these pins out, and I want to connect this over here. This part name I can keep separate, and then I have the C which is connected over here. Okay, right? And then I have CB which is to be connected here, and then I have the ground which is connected over here. So this is my ground pin. Sorry about this. Select ground. Come on. Okay. 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 And then I have the VDD is connected over here. You can keep part name below if you want. Instance name here. And what did I move here? Sorry. Okay, I don't want this guy. And I want to shrink this here. Okay. So here I want to put in a bubble. Okay, so I'll put in a bubble here. Okay, now I'll just the part name, instance name. Okay, fit. Okay, so I have made a TX cell. Let's see if I'm recording. Okay, so if I do check and save, everything is fine. This is a TX cell, and this is the symbol for TX cell, and we are ready in business. Okay, now what do I need to generate? Okay, I need to generate a D latch. Okay, and I need a NOT gate. So I need to make a category here which is called static. So I'm going to put all static gates in that. Okay, and here I'm going to make a new cell, and I will call this as not G, not G, which is basically a NOT gate. Okay, and NOT gate, I am going to use a simple PMOS and MOS. Sizes I'm going to keep as 3 times, right? Okay. So let's make a NOT gate. So I'm going to just copy those components from, or I can insert them, doesn't matter. Okay, so let's do an insert, and this is PMOS device, and I need 3.5 into 6, let's say. And where these numbers come up, 3.5. Okay, and number of fingers is 6. These numbers are coming from optimized output, so don't worry about that. This I can close. So just do that. And then I want the NMHP, which is going to be 2.5 times of what happened. Okay, let's do this again. There's an error here. Okay, let's do an insert. Finger width is 2.5. And number of fingers is, let's say, 4, so that makes it 10 micron device. Okay, so this done. I'm just going to make connections. So this sits in the valve, so it's connected like that, and this is connected like that, and that's a very simple NOT gate. I need to just create the pins. So you have got A, then you have got VDD, or I would say ground. Let's see how it rotates. So that's a ground. Then you have got P sub. That's a P sub, substrate contact. And then you have got Q. Okay, so I need to rotate this. So you need a Q, and then you need a VDD. So I need to rotate this VDD. Okay, so let's connect all the pins. Okay, so that's your static NOT gate, and I'm going to make a symbol for this one. Sorry for closing it. Okay, so let me just open this again, and that's going to be a NOT gate. So left pin is A, right pin is Q, bottom pin is ground, and bottom pin is P sub. And then the top pin is VDD. Sorry about that. The top pin is VDD. Okay, so we're done with this. And I'm gonna make a symbol for this, a very concise small symbol, because I'm gonna use this. So I want to just do a small symbol like that. So that's going to be my NOT gate. So part I can keep outside. This I can keep here with a small bubble. And this one Basically this one I don't require, so I am going to just delete this. Okay, that shrinks here. This is ground. Of course, I'll move. So this is ground. This is P sub. And this is VTD. Correct? And then I'm going to create a small bubble. The bubble goes here. That's the instance name. That's the path. Okay, and do a check and save. Done. And check and save and done. So we have the blocks, okay, ready for the delatch. Now we also need an AND gate. Now the question is, I can have a NAND gate and a NOR, which can all act as a AND gate. And so that's what we're going to do. So let's make a NAND gate first. And this is a temporary design because ultimately I'm not going to use NAND gate. Okay, so I'm going to make a new cell and under I'll call this as NAND G. Okay. Now just one second. Okay. So I am going to do okay, and NAND. So I am going to take a NOT gate and copy some stuff from there. I am tired of placing stuff, so I'm just going to copy this. So I will say C, and I am going to copy this over here, and I will modify this to be an AND gate. So I'm just going to copy this to the side like this, and the size is 2.8 into 6, like two. Sorry about that. 10. Okay, so I want to make this as 2.8 into 2 into 6. Sorry, 2.8 micron. Okay, and this one also Q 2.8 micron. Okay, and this one is 2.5 into 2. So Q 2, oh 3, sorry, 2. Okay, so I want 2 of these, right? So I'll just copy that over here, and I'll just connect them out. So this one is VDD. This one is the output, and this one is in series, and This one is P sub, and this one is connected here, A and B inputs and ground. So now let's put in the pins. So I have got A here, then let me just draw this way. Okay, so that's A. Then I have got B, that's over here. Then I have got ground, which is over here. Then I have got P sub, which is over here. Then I have got Q, which is the output, which is over here. And then I have got VDD, right, which is over here. Okay, so I'm just going to connect them. A, B, ground, P sub, Q, VDD. So we are all set with this. I will do a check and save, not issue, and I'm going to make a symbol for this one. So create self view, from self view, make a symbol. So on the left I have got A, and then I have got B. Sorry about that. I have got B. So I have A and I have B. Then right side I have Q, and down I have ground, and I have got P sub. And on the top I have VDD, and say okay. So now I am going to make a small, again I'm interested in a small block. Okay, and I am going to move the path name out of the way. I'll bring in Q here. This one I can delete. Come on. And P sub and ground, right? So ground, P sub, they go here, and VDD goes in here, and this moves here. And I'll put a bubble in here. That's done. Check and save. That's a Nand Gate. Done. Now, I also want to make a NOR gate, and I might use it somewhere. So it's a modifier. So the name gets added here. Okay, so let's make file new cell view. So I'm going to call this as NOR gate. Okay, in here I'm just gonna copy these guys. You see, now I'm gonna place them here, turn it into a NOR gate, and I might use it. So I'm just creating that just in case. Okay. Okay. So I am going to reconnect them. Right. So this guy goes off. This guy goes off. And let's disconnect this one too. And this guy goes on top of this guy like this. And let me disconnect this one too. And probably this one. And then this transistor goes in parallel here. And I want to change the size here. Q. I will call this as 4 into 2. Apply. And similarly over here, 4 into 2. Okay, so these are 8 micron devices. Okay, so let's make the connections. So this connection goes here. This ground connection goes here, and this substrate connection P sub goes here, and this connection goes here, and we are done. So that's your NOR gate, and I am going to put the pins. So I am going to have A over here, then I'm going to have B over here, then I am going to have ground over here, and then I'm going to have P sub over here, and then I'm going to have Q over here, and then I'm going to have VDD over here. So I have got A. Well, let's bring this down. Then I have got B. I have got ground. I have got P sub. I have got Q, and I have VDD. So this is our checked in save NOR gate. So create cell view from cell view, and inputs are A, B, right pin is Q, bottom pin is ground, and P sub, and the top pin is VDD, and we are done. Okay, so I'm going to make a very small NOR gate. Okay, and this guy goes off. Come on. So this guy goes off. Path name comes here. I'm just going to connect ground and P sub. So that's a ground and a P sub, and that's a VDD, and that's a queue. That's the instance name, that's the path name, and we are done with the Nand Gate. So a little bit of adjustment. And a bubble. Okay, so that's a Nand Gate. Check and see. Done. Check and see. Okay, probably have all the ingredients for 2x3 cell. So let's make a 2x3 cell. So here I will make this as another category called subcircuits. Okay, I will call this as subcircuits, and I am going to make a new cell view and call this as cell 2 by 3. Okay, okay. So I need to make a master slave delatch. Okay, using transmission gates and NOT gates. It's very simple. So what I'm going to do is I need a transmission cell. So I'll just do an insert and browse, and this one under TX gates I have a cell. So that's one cell. Okay, and then there is a feedback path. So I am going to flip this. So that's the feedback path. And then I'm going to have a NOT gate. So under static, I'll put a NOT gate. Okay, okay. And then I can connect it like this. Okay, so that is a latch. Okay, and I will connect these in tandem. So C would be connected with C bar over here, and C bar is connected with C. And then you can run all the grounds together. Sorry about that. And you can name them also if you want. So let's run all the grounds together. Right, so that's a ground, right? So all grounds are running together, right? And then all supplies running together. Right, so here is the supply. You can route it anywhere. Okay, you can route it like this also. So these are all the supplies connected, and then I have P sub over here, which has to be connected to P sub over here. Sorry about this. I'll hit this. Just one second. Okay, so we have all the connections done, and this is a D latch. Now, this is a master. Then I'm going to have a slave, right? So I'm going to copy this stuff and have a slave here. Only thing is that I have to flip these connections. These connections I need to flip, right? So one is driven by clock, other is driven by clock bar. So that's a clock bar, right? That signal is a clock bar signal, and that signal is a clock signal. Okay, and then this goes to this, and then VDDs connect together and grounds connect together and P subs connect together. Correct? So that's a D flip-flop. So let's make it bigger so that we can see it. Okay, so one is a master, other is a slave. Now the question comes is, okay, so I have to put an AND gate here with the NAND gate with the inverter versus an AND gate, and then take the bar from here and feed it into here. Now, can I take a NOR gate and invert both the inputs to make a AND gate? Yes, I can do that, right? Yes, okay. So one thing is that. The other thing is, why do I need some blocks in here? For example, I want to cut the delay on this forward path. So instead of picking up through this NOT gate, I can pick up from here somewhere, right? And then, so I can modify this, right? So we will do that, okay? So I can get rid of this NOT gate over here if I pick up from the output from here. And then I might not need even this cell because this can act as a floating node, okay? And a floating node, if the leakages are minimized, then I can even get rid of this transmission cell to make it faster. Okay, so I'll do that first. So I'm going to get rid of this cell. Okay, and I'm going to get rid of this one. Okay, so now I'm picking the input from here, and there is no feedback. So I can delete the feedback part. Okay, so that part is gone. This supply line is gone too. So this is being done for the speed. Okay, I have cut short the size of the circuits. Okay, so now one inversion has taken place here and one inversion over here. So that means that this node is Q now instead of that node. Okay, and another thing which I want to do is to increase the speed is I want to make some differential gate with a positive feedback. Of course, there's a warning. Don't worry about that. Okay, so I'm going to replace this guy with a differential NOT gate. So how do I make a differential NOT gate? So I'm going to make a new category, and I will call this category as PPCL, push pull complementary logic. not. Okay. Oh, okay. So I would suggest say PPCL first. PPCL. That's a category. Say new cell. I'll call this as PPCL not. Right. And say okay. And I want to make a PPCL gate, push pull complementary logic, which is based on positive feedback, okay, or cross coupled or a negative generation. This is being done for improving the speed of the, the forward path. Right. So let me just create that. Okay. So for that, I just need an NMOS device. So let me see how much time I have spent. Spend 1 hour to create this 2 by 3 cell. Okay. Uh, well, let me take my time because this is a key to the operation of PLL at high frequency. So let me take my time here. And here I am going to put in NMOS devices, MOSFETs, HP, and I'm going to create two sizes here. One is going to be, okay, 4, 3, 12. Okay, so let me make it 3, and I keep the number of fingers as even 4. So that's a 12 micron device. Okay, so I need 4 of them. 1, 2, 3, 4. And these are N, so let me just connect them out first. This is the supply, and this is the ground. And these are the subs. So before that, let me put here what you call uh, a negative resistance circuit, which is going to be cross-coupled PMOSes. So let me insert a PMOS here. So I PMHPRF HP, and I need 2.8 into 6, 6, 16. Okay, one goes this way, other goes this way, and they can be connected because they are sitting in the well. You can connect the body connection to the source, but here I'm going to cross couple them. So this is your cross coupling, and then they are supplied from the supply, and one of them is pulling this leg and other is pulling that leg. Okay, and then one of them is A, other is A bar. Yeah. So that's A bar, and then you are going to have Q and Q bar and VDD and ground. So we are done, but then we have P sub also. Let's connect those also. So that's a P sub, that's a P sub. So let's just put the pins there. So I have got pin A, which is going to be this one, then A bar, which is AB. So this is a differential NOT gate. So that's AB, and that's a correct. And then I need a VDD. So where is this? VDD. That's over here. Then I need a ground. That's over here. Then I need a P sub. Okay. So P subs have to be connected together. So that's a P sub. And this P sub has to be connected with this P sub. Correct. So this is P sub. And then you have a VDD connection. Okay. And then the thing which remains is Q. Okay. Yes. Okay. So I need a Q and a Q bar. So Q, Q and a Q bar. Sorry, and a Q bar. And this one is a Q bar, and this lag is a Q. Simple, right? So we do a check and save on this one. One warning. Oh, ground is not connected. So that's the ground. Do a check and save. We are done. Now I'm going to make a symbol for this PPCL, NOT gate. So I am going to do a PPCL NOT gate. Okay. So I have input pins as A and A bar as a left pin, Q and Q bar as the right pin, ground and P sub as the down pin, and VDD as the top pin. Okay, and say okay. And I am going to modify this a little. So I am going to make it a NOT gate. And I need to move stuff. Right, so I'm going to move this out of the way. This goes in here. Okay, this is Q. Sorry about this. This is horrible. Okay, this is QR. Okay, I'm going to add a bubble here for QQ bar. And this is your ground. This is your P sub. They are over here. And this is VDD, which is over here. And we are done. This guy is not required. Okay. So this is an instance. This is a part number. And I need to insert a small bubble. That's a small bubble. That small bubble goes in here It is too big. Okay, doesn't matter. Okay, so this is check and save. That's your PPCL NOT gate. Okay, so what am I going to go do to this 2x3 cell? I'm going to delete this guy. And I want to put here a PPCL NOT gate. Okay, so don't worry about which connections are what right now. I will explain you what are those. This is your P sub, of course. So I am going to insert a PPCL NOT gate. Insert, browse, and I have to look at PPCL. Of course, it is uncategorized. Okay, so there goes your PPCL NOT gate. Okay, so I'll just make some connections. This goes to VDD. This guy goes to ground, which is over here. Okay, and this guy goes to P sub, which is over here. P sub. Okay, so I did some mistake here. Okay, done. Okay, so now this connection goes in here, and of course this connection will come from the bar, right? Okay, and this feedback is supposed to be there, right? So feedback is going to be between Q going to feedback. So this is going to be feeding back to the NOT gate, right? So this is a feedback, right? So that feedback will come from here, right? And then this basically can come from this node, right? So how would I connect that node? From the top? From the top, maybe. Maybe I'll go this way. Of course, so this is how you are driving a PPCL gate, right? Okay, so let's clean up this. So delete, and clean up this guy, and this guy, right? And now see what has happened. Okay, now I'll show you what has happened. So we got rid of one gate over here and a feedback path. We still have that. That means polarity here is reversed. So this node is a Q and this node is a Q bar, right? So this is a Q bar, okay? And this is Q. So I need to feed it back with a NAND gate. So if I take a NOR gate and invert both of its input, then becomes a NAND gate, right? So, okay. So I am going to take a NOR gate here. So the logic is very simple. The logic is same as this one. It's just that this AND is implemented with a NOR with both input inverted, right? And then the Q bar is supposed to feed in here. So basically we'll feed in Q because NOR gate has to be, inputs have to be inverted. So I am going to go here, browse, and I'm going to bring up a NOR gate, right? So I bring up a NOR gate over here and I'll connect its VDD, which is here, and it's ground. This is your ground connections and the P sub connection, right? So this is your ground connection. This is your input. This is your P sub connection. And this guy is supposed to come from Q, which basically means this node. correct? Okay, so we are done with this. So this is a Q bar. So I'm going to start putting pins now. Okay, so we will call one as VDD, which is over here, and then we have a ground, ground, which is over here. Okay, and then we have a P sub, which is over here. That's the P sub. And then we have a clock, which is this one. So we have a clock, right? So the clock I am going to put here. That's driving that. And then we have a clock bar. Okay, which is driving this guy, CB. So let's put it here. So that's driving CB. Okay, so now we have the top path ready. Now we are supposed to make a swallow circuit, right? Okay, we are going to call this as QB. So let's do that. QB and Q. QB. So that's a QB. And then we have a Q. That's a Q. QB, Q. Okay, so now we are going to make a swallow path. Okay, so the top design is over. So for the swallow path, I'm again use a NOR gate with an inverted in, okay, as an AND, right? So let's do that. So put a NOR gate, insert, and I want NOR gate as an input. So I will connect this guy to VDD. Can I bring from outside so that we can be consistent? VDD, and then this guy is ground, which I can get from here. That's a ground, and then there is a P sub connection. P sub connection is over here, but I want to bring it from this side. So that's a P sub connection, and this one is supposed to come from Q. As you can see in the diagram, it's coming from Q, but then it has to be inverted, so it will come from Q bar. So this will come from Q bar, which is over here. Oh, right. So that will come from Q bar. So ultimately, if this works or not, doesn't work, we will see later on. According to me, I'm doing nothing wrong as at present. I hate this dividing. Okay, I'd rather pull these pins out. Okay, so now I want Q bar fed into A, and then I have a NOT gate to bring in mod in. So I need to insert a NOT gate. And it goes sideways. Yeah, escape. So that's a VDD connection. That's a ground connection. And that's a piece of connection. Right. And I hate this when this happens. Okay. I hate this when this happens. Right. So that's fine, right? Everything is connected. That's that. And this pin is going to be M in or mod in. M in. Oh, oh, okay, doesn't matter. I hate using min and max. It can conflict. Okay. So that's your input. And then you need again a transmission cell, because this is going to be a rudimentary master on this side. And that transmission cell is driven by the series transmission cell, right? So that's driven by clock, in clock part, right? So I am taking the same masters here. The rudimentary cell over here will serve as a master here also, right? So let me insert a TX cell, TX gates, a TX cell, right? And I want this sideways. Okay, so that comes out as a rudimentary gate, and this is driven by clock, correct? And this is driven by clock bar. Uh, this is a clock bar, right? So what to here? I hit this. This is a clock bar, right? Right. Okay. And then of course there is VDD and ground. So I will borrow my VDD from here and my ground from here. Okay. So this is done. Okay. So this is my rudimentary master. And then I have a slave. Okay. And all that slave has is just a mark and right. So if you remember, here there is an AND gate. I will implement this a NAND with inverted output, right? So I will take a NAND gate, okay? So I will take NAND gate. To some people it may be boring, but I can't help it, right? So that's an AND gate. So this one is P input, and this is M in, so this is P input here. Okay, so I am going to put in a pin here, which says this is going to be a P input. Okay, so that's a P input. Okay, and then I'll just make all the connections like VDD in ground, right? So that's a VDD, that's a ground. Of course, the P has come in the way. Let's pull it down. Okay, so this is my ground, and this is my P sub. Done. So this is connected, and then I have a this is has to be AND gate, so there has to be inverter here, right? So I will say, what was that? What did I do? Escape. Whoa, what was that? I am totally unaware. Okay, I'm gonna just save it and exit it, and I am going to create 2 by 3 cell. Okay, I don't know, I pressed some button. Wait. Okay, so all I need is a NOT gate. Insert. Okay, check label attachment. Okay, I want a NOT gate here. Sideways. That's a NOT gate. And there has to be a mod out. So I'll just connect VDD, ground, P subs. Of course, there is a P sub here, which connects here. Escape. Okay, so now everything looks fine. There is a again a TX cell here. Let me see if all the TX cells are in right direction. Right. So there's another TX cell in here. I browse under TX gates. I have a TX cell. I'll move this sideways so that it's facing the right direction. Fine. And I'll just make the connections here. Let it make it bigger so that people can see it, what I'm doing. Okay, so here this guy is driven by VDD. This guy is ground, and this is driven by same as this guy. So this is CB. Okay, so this is CB and this is CB bar. So this is going to be CB clock bar. So that's over here, and this side is going to be clock, which is over here also, right? So this is a clock, right? Why can't I run a clock this way? Clock and clock bar. So this is driven by clock bar. Correct. So this is done, and this guy is going to feed to this one. So this completes. This would complete my high speed 2 by 3. Now there would be one mod out, which is nothing but the output of this guy. So this is a mod out. Other than that, we have everything in place. We have a VDD ground and everything. P sub, everything is there. Just mod out is not there. So let's put in mod out. or M out. Okay, and that's over here. Oh, now I can do a check and see. Uh, what's the error? One error. Uh, Error exists. What's the error? VDD is an error. What kind of error is that? Can't tap the clock bar with net VD. So somewhere clock bar is, so this is clock bar. Oh, this connection is wrong. So this is a wrong place. Okay, sometimes stupidity is creeping here. This is not VDD. This is clock bar. This one, right? And if I do fit and I do check and save, we are all set in business. So this is our 2 by 3 cell, which is in some way equivalent to this 2 by 3 cell. Nothing special in here. It's just that it's going to work at high frequencies. So I'm going to make a symbol out of this. Okay. So let's make a symbol for this one. Subcircuits, modify 2 by 3 cell. Let's look at uncategorized PPCL, modify PPCL not. Okay, so we have everything categorized. Now I want to make a symbol for this cell. Okay, so let me see how much time I have spent. Oh, 1 hour 32 minutes. Hang on a second. Okay, so I'm going to make a symbol for this. Create cell view from cell view. And this is kind of involving, but I can't help it. You know, if you want to do circuit design, you have to live up with this kind of stuff, right? So on the left side, I'll keep clock and clock B. And on the right hand side, I will keep, okay, I also want to keep P sub on the left. Huh? Do I want to keep P sub? No. I want to keep mod out or mouth on the left so that I can cascade it. Okay, mouth on the left. On the right, I want to put Q, sorry, not Q, QB, and min. Right, and at the bottom, I want to keep P ground, P sub. P ground and P sub on the bottom. And on the top, there will be VDD. So let's see what I have used. I have used ground, I have used P, I have used Q bar, VDD. Then clock on clock bar, I have used already. Min, I have used. Mouth, I have used. P sub, I have used. Okay, okay. So here, I'm going to make very small changes, not big changes. This one, I'm going to move up. And this one, I'm going to move down. And I'm going to separate out this slightly like this, and this I will center it out, put the instance name here, path name, move clock up, clock bar up. I want to insert edge triggered stuff. Similarly over here, this is edge triggered, and then I want to put a bubble here, a small bubble here to mark that this is a inverted input. That's it. That's a bubble. That bubble sits here. So I guess I'm done with most of the stuff on which you can see. Now I want to test this. So this is the moment of truth. So I'm going to make a new category. I'll say test benches. Test benches. Mm, say OK. And here I'm going to create a new cell and say test 2 by 3. Test 2 by 3 cell. And that's what I'm going to test. And here I want to cascade two 2 by 3 cells and see its performance. Okay, so let's modify it. Test 2 by 3 cell. Okay, so I want to insert 2 by 3 cell. Insert on the subcircuits. You have a 2 by 3 cell, and I want to take two of them and cascade them. Correct? Okay, so here I can be a little quick because I have to just test it and show you. Okay, so they are in ripple. That means Q is driving clock, Q bar is driving this. This is VDD. This is ground, and P subs are also grounded. This is mount. This is min. And let's load this. Okay, let's load this with something like a big capacitor. Let's say 60 femtofarad. For each cell, something like 60 femtofarads is there. So I will go here, go to analog lib, and put in a cap, right? And the cap shows up here. So I'll make it 80 femto, 80, or rather 60 femto, 60 femto. Correct? So that's a 60 femto load here and here. And then I need a ground. So that's a ground over here. That means that these guys are grounded. Right? And M in I am going to, for now, of course, M in also I'm going to give a supply. So let me put in VDC, insert VDC. Okay, and put in a 2 volts voltage. Okay, so this is being driven by a 2 volts drive here. Okay, I hit that. That's okay. And then I have to put clock bar P0, P1. So this will be P0, that will be P1, and this will be your M in to enable or disable. So when M in is high, then P0, P1 have a meaning. Otherwise, if M in is low, it's always divide by 2, so the net is divided by 4. So the net is divided by 4 when M in is low. When M in is high, then P0, P1 will come into picture, right? So let's put here clock bar, and let's be a little tricky here. So I want to put V pulse, right? So let me insert V pulse. Okay, there's a V pulse here. Okay, so I want to put voltage 1 is 0, voltage 2 is VDD. Well, in this case, I should create VDD, so I would do a VDD here. VDD. Okay, so that's fine, and this should also be VDD. Period is 1 over FC. That is my operating frequency, 1 divided by FC. Okay, and delay is nothing. rise time is 1 over 100x. So rise time is 1/100th of the uh, time period. So this is going to be 1 over 100 into f, right? So fall time is 1 over 100 fc, the same stuff, right? So copy, paste. Okay, rise and fall time, and the width is going to be 1 over twice of half of 1 over fc. So this will be Control C, Control V, and here I will make 2 times of fc minus the rise or fall time, whatever you want to take. Control C, Control V. Okay, so that's all that is, right? And that's my clock. And clock bar, I'm just going to change. Uh, I'm just going to change VDD and 0. Okay, so just bear with me a second. Okay, so here let me just connect them first. Ground, ground, and here I am going to just swap, sorry, not sweep, swap. Okay, I will name this one as VDD and this one as ground. Let's see. Okay, so we are now in tandem, and here I'll put a 10 femto. Actually, it should be floating, but let's terminate this with, this is the final mod out. I'll make this as a 10 femto because it's just one transistor, right, inside the design. Okay, so that's a 10 femto, and this one I'll call as VDD. Okay, so we are in business. Now we have to drive 3 clocks more. So I'm gonna take this guy and I'll put one here and change this. Just 1 second. Okay. So that's driven by ground, and I will have this as 40 over FC, and this one is what? Okay, 40. Here also I'll put 40. So that's half. Okay, so that's that. This one I am going to make 80. So I'm generating all the states. Okay, so if I go Q here, this one I'll make 80. This is 80. Okay, so that's also done. Okay, and this one I'm going to keep the next one very large. Just 1 second, bear with me. This one I'm going to do 160, the next one. Okay, uh do I need to check something? No, just copy this. So I have generated 8 states for 3 inputs. Okay, by the proper time periods. So this one is going to be 160, 160, 160, 160. Okay, so we are ready for simulation. Okay, unless something goes very wrong, I will not have a bad answer. Okay, so in this case, I'm going to read the variables from the cell view, which gives FC. And let's say this operates at 6 gigahertz. Okay, 6 gigahertz. And supply, let's say, is 2 volts, correct? And then I want analysis choose, and I want to do a transient for 320 nano, 320 nano, because I want 2 cycles, right? 320 nano conservative, and I want to save the following outputs. Okay, I want to look at clock. I want to look at this one and this one, and I want to look at this one and P1 and P0. So we have saved that, and we are going to hit simulate, unless something for a blunder, I don't know. So what did I do here? Issue condition, it's doing it. Okay, what did we do? Let's summarize. I created a 2 by 3 cell which can operate to a high frequency, right? And I think it's going to work up to 6 gigahertz. And I am cascading 2 by 3 cells. That means that the base count is going to be 4, and then depends on P0 and P1, it can be a count of 4, 5, 6, or 7. Right? So let's verify that. So let me put you on a hold while this is being done. Okay, so simulation is complete. I just wanted to, highlight that I tried 6 gigahertz, and that's basically exceeding the what highest operating frequency is. So I'm going to try this at 5.5. I have simulated this operating from 2 volts, and I am going to look at the output now. So I go to direct plot from main. I'm sorry. Okay, so let's go ahead and plot the clock. So that's a clock. I've simulated for 100 nanoseconds. Next, I'm going to put in this guy and P1 and P0, and I'll just split it, and I'll put the output. Okay, so now let's go ahead and zoom in. Let's zoom into this piece. Okay, so in this region, I have got M in as 1. So divide by 3 is possible. So let's pick up, the transition takes place here. So let's pick up this one. 1, 2, 3, 4, 5, 6, 7. So here 1, 1, that's 3, count of 3, added to the base count of 4. So the division is by 7. You can count again. 1, 2, 3, 4, 5, 6, 7. And then again starts 1. Okay, so this is when 1, 1. Let's look at 1, 0, which is in this region. So let's count here. 1, 2, 3, 4, 5, 6. And then again 1, 2, 3, 4, 5, 6. So in this region, it is 1, 0, which is 2 on top of base count of 4, that is 6, right? So let's look at another one, which is over here, 0, 1. Okay, so this is going to be 0, 1. So in this case, 0, 1 means it's 1 on top of 4. So that is 5. So we can count. So it's a transition over here. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. So here it's dividing by 5. Let's look at 0, 0, which is over here. And in this region, it is 1, 2, 3, 4. 1, 2, 3, 4. So it's dividing by 4 here. And let's look at mn is equal to 0. So in no matter where you check here, it's always going to be dividing by 4, right? 1, 2, 3, 4. 1, 2, 3, 4. So anywhere it's going to divide by 4. So now this 2 by 3 cell is operational up to 5 gigahertz, 5.5 gigahertz, and our VCO is operating from 3.8 to 4.8, so it's well within the limits. So now the next step would be to make a 5-bit or maybe 6-bit if you want. Make a 6-bit 2 by 3 or multi-modulus divider. So I'm going to do that next. So what I'm going to do is I am going to just cancel all this. I know the 2 by 3 cell is working, right? So I don't want to save this. I don't want to save this. Okay, everything goes off. And I am interested in making a multi-modulus divider. So I'm going to make file, new, cell view. And here I will call this as MMFD. MMFD. And this is going to be 6-bit, right? So it's your choice here. You want to make a 5-bit or a 6-bit. This is going to be taking the course count. Okay. So I'm going to do that. And here I am going to just take 2 by 3 cells. If I do insert and if I browse here to generic subcircuit 2 by 3 cells, so I can connect 4 of them like this. And notice that all people at this frequency, at this node of 130 nanometer, they start using CML. And CML consumes a lot of power. And my idea is to reduce that power consumption, so I'm not using any CML. So here I have all transmission gates or static gates. Right, so I'll just cascade them like this. Okay, and then this can be mod out as mod in, 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 mod out as mod in. And then these are all supplies, so I can just bunch these supplies over here. So these are all supplies, right? So these are all supplies. So bear with me. Okay, so these are all supplies, and let's just zoom in. Okay, so these are all supplies connected. Then these are all grounds. So let's go ahead and connect the ground. So these are all grounds. Sorry about that. So my idea is I want to load the VCO and see then how it forms. Okay, so here that's a P sub for all of them. That's a P sub. That's done. And then these are P's. This is clock. This is mod out. And so I'll just put the pins in here. So I will start with VDD. Okay. So that's a VDD. And let me just shrink this. Okay. Then I need a clock. So that's a clock. Then I need a clock bar. Okay. So that's a clock bar. And then I need a mouth. That's a mouth. M mod out. Right, so that's a clock. That's a clock bar. That's a mod out. That's a VDD. Then I need ground. So I need a ground. Okay, ground. Hang on a second. Ooh, touch screen. Ground. So that's a ground. And then I need a P sub. Of course, you can put in here the resistive model of the substrate on P sub. Some processes give you a what you call a P tab for inserting the losses, right? So this is your P sub, and then you have got all the, hang on a second, then you have got all the P0 P1 pins. So I am going to put here P0 sideways. So that's a P0. Then I want a P1. So that's a P1. Then I need a P2, and that's a P2. Then I'm just going to connect them first. This is P0, P1, P2, and then P3, P4, P5, right? So again, pin P3, that's a P3, sorry about that. P4, I rotate it this time, that's a P4, and then you have got P5, and that's a P5, and I need to rotate this guy. So escape, rotate, and just connect it. P3, P4, and P5. So this is going to divide by 64 to 128, 64 to 127, sorry. And these are going to be again Q, Q bar, Q bar, and then I am going to have M. Okay, so I'm going to just connect them. Q, Q bar, M. Right. So we are done with this, right? And I'm going to say check and save. Okay, and I'm going to create a symbol for this one, so there's no error here. So create cell view from cell view, and okay, and here I want to put left pins as clock, clock bar, clock, clock bar, and then I'm out. right? And the right pin says Q bar, and amen, right? And the bottom pins are going to be uh, ground, P sub, and then I will go with P5, P4, P3, P2, P1, and P0. Sorry about this. P. Okay, so I have consumed a ground P0, P1, P2, P3, P4, P5. I have consumed QQ bar. VDD is on the top. I have consumed clock bar, min, mount, and I have also consumed P sub. Okay, let me say okay, and that's my symbol. And I'm not going to do much to this other than I would just separate out these and separate out these. Oh, I made MO in. Okay, typing mistake, but I'm going to leave this as is. Okay, I'm going to say it's check and save. 4 warnings. What are the 4 warnings? MO in. Oh, it should be called M in, right? Let me see, what did I call it here? M in, right? And this is MO in, right? So I'm gonna do save this, but I'm gonna go here, create cell view. From cell view, I should be able to edit it, right? Create cell view, pin list notepad. Can I not modify this cell view from cell view? It says modify. And yes, and here I need to just throw this guy out. So I will just put a delete. Okay, so this was the pin which was in error. So I'm just going to select this guy and rotate it out once, right? And again rotate this and rotate this. And then I am going to move this here as ammo, delete this guy and save it, and say check and save. So this is done. Okay, so I have done a check and save here, and wait, check and save here, and this is done. Now, am I going to test everything from scratch? Well, I am not. What I'm going to do is I'm going to take a test 2x3 schematic, and instead of this I am going to just put your multi-modulus divider. So I'm going to throw this out, delete, delete, delete these guys, and P I'm going to give as static now, because P hardly changes. It changes when you configure a PLL. It doesn't change later on. Okay, so I'm not going to give a dynamic input. So I do insert, browse, and I will go to uncategorized and MMFD. So a clock is being driven like that. So everything looks fine. And this guy is driving that. This is that. And here P sub and ground is there, right? So P sub and everything I'm gonna ground. So I'm going to just simulate the first and the last state. So the first state is going to be all zeros. All the P inputs as zeros, right? And M in as VDD. Okay, let me just delete that. So we are all set with this. Okay, so this is a static case. Okay, I'm not going to change P0 to P5, and I'm putting all of them 0. That means that this is going to divide by 64, right? And this is enabled, and everything looks okay. Check and save, launch. Okay, so I'm going to read from variable, read from cell view. FC I'm going to keep as 5.5 gigahertz, and VDD I'm going to keep as 2 volts. And the output to be saved, select on the design, which is going to be this output and a clock. That's it. And then I'm going to have analysis as transient, and here I am going to put 100 nanoseconds and conservative and say okay, and I'm ready for simulation. So I'm going to put you on hold after simulate. Okay, so this is simulating. I'm going to put you on hold and come back when it is done. Okay, okay, so it seems like I'm done, and what I'm going to do is I'm just going to plot this. So I'll go to results, and somehow this time you have to lift with a bad audio because I had my mic connection had a problem. So I'm going to take a clock, and I am going to take this guy, and I want to check if I really am dividing by, I'm really dividing by 64. So I'll start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and twice of 32 is 64. Correct? So that's done. And I'm going to do one more simulation where I am going to go in and modify this to be all ones. So what I'm going to do is delete. So I'm going to delete all these, and I'll connect all of them to 1. So basically I'll be connecting this to 1, and that means that it is going to divide by 127, and I'll roughly see that. Okay, there's no point in counting that. So I'm going to save this, and I am going to run this simulation, and once it starts I'll put you on hold. Right, so it started. Okay, and I'm going to put you on hold. Let me see. Yeah, I'm going to put you on hold. Simulation is done, and now I have a waveform where I can count, but it looks stupid to count. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I give up, so I don't want to count. So seems like you can plot the frequency response and look at whether this is 127 divided by 127. But notice that this is asymmetric. Now another thing I assume is I have this, which is 32, and I can fit 3 in here, so that will be 4 times of 32. So that would be roughly 127. So it looks like it is going to be 127. So I am going to stop in here, And I really apologize that my mic has a connection problem, so my audio may be bad. So, anyways, thanks a lot. So that's multi-modulus frequency divider, operational up to 5.5 gigahertz, and the VCO will be driving that. So we will see that in the next circuit, and we will see the output stage of the PLL, which is 2 by 3, is up converted to F naught with a quadrature output. So that's what we are going to see.